the rest of the class and just work through sort of basic overview of general linear model type of stuff. So show of hands, like how many people sort of thought of needing to figure out like what analyses to use for my thesis or dissertation or some other such business seems really daunting and difficult. Okay, right? Determining what analyses to use to answer my research question is actually a pretty straightforward thing as long as you sort of know what are my IVs, level of measurement and how many, and number of DVs that I have, level of measurement and how many of those. Once you've got that stuff figured out, everything else kind of falls into place. For the types of inferential statistics that we do, both the stuff that we've done last semester and moving forward into more complex types of things, this GLM is going to be kind of your basic approach to the fundamental building block. That's why we're going to spend so much time on regression this semester, so that you have a really, really strong foundation in that, and then we can start to jump into multi-level modeling, things along those lines, or late class analyses or things along those lines of stuff, so that it builds off of that, okay? So, just as a review, last semester, we talked about independent sample t-tests, right? So we're looking at differences between two population means, right? The idea is that we have two unknown populations whose parameters we don't understand. We're taking samples from those and saying, do these data that we've got, if we've got good representative samples from population A and population B, let's just say men and women, just make it easy, right? And we are looking at extroversion, right? We don't know what the population value is for men and women on extroversion, right? What we can do is we can pull samples from men, pull samples from women, and use those samples as representative of their respective populations, right? And then what we're doing with our analyses is saying, assuming the null hypothesis is true, assuming that men and women do not differ in terms of their overall levels of extroversion, what's the probability of getting samples as discriminant as these, right? And if they're relatively close, right? If the means don't differ more than we would expect just due to basic sampling error from pulling two samples from populations with equal means, then we say, well, we don't have much evidence of a difference. But if they are much, much different, right, then we would start to say that the data are giving us some evidence that it's likely that the population values from which these two samples were pulled are not equal to one another, right? So this is our basic independent sample t-test. Questions on independent sample t-test? This is all coming back to people. Also talk about our paired sample tests. Here, what we've got is we've got we've got one population. We're just measuring on multiple occasions, oftentimes after having done something in between the first and the second assessment. Here, what we're looking at is we're looking at the mean difference score in the population, right? So if I'm looking at the reliability of depression, right? Or let's use something else. How about aggression? How about that? We want to know, is aggression kind of a stable thing, right? And so we take aggression and measure it once, measure it again a month later, and so hypothetically what we're talking about is some different score. Some different score. This population, let's say it's all individuals, if we were to measure aggression once and measure it again a month later, there's some score, right? There's some different score. And what we're interested in our paired sample test is whether or not that different score is some value other than zero. Does this change across repeated assessments, right? So our null hypothesis for a paired sample test is that the population of different scores is zero. Our alternative hypothesis is that it's some non-zero value. There's some change if we measure things on multiple occasions, okay? So once again, we don't have access to the population difference score, but what we can do is we can pull a sample, measure individuals in that sample on multiple occasions, and then go through and sort of draw some conclusions from there. So usually when we're talking about a paired sample test, we're talking about measuring the same set of people on multiple occasions. When else can we use a paired sample test that's a little bit different? Do we remember?
Some sort of matched groups on.
Yep. Matched groups, right? If we've got, say, this group, and this is often more common in, like, I think in marketing and econ stuff, right? Where we can't we can't measure the same people twice, but what we'll do is we'll take this group and we'll get a bunch of characteristics that we think are important and match people on age, gender, income, sort of whatever, and then we can use this same thing because we're saying, well, if CJ's in my first sample and then I find some other random person that has his same age, gender, preferences for sort of a bunch of other stuff, we're going to treat that person as functionally equivalent to CJ for all intents and purposes, and then we can use the same match pairs, stuff like that. And there's sort of interesting stuff and controversial stuff with propensity matching protocols and things along those lines that do some interesting stuff here. But for psychological science, generally the types of things we're doing is measuring people on multiple occasions. Right, and then we talk about ANOVA stuff, right? Review here, what we're doing, basically same questions that we have as our independent sample t-test, except now we're just looking at more than 2 populations, right? Remember that our t-test is just a special case of ANOVA, right? Nothing much different here. With ANOVA, we're just looking at population 1, 2, 3. Again, we don't know the characteristics of these populations. What we can do is we can pull good samples from each one of those populations and look at differences across the samples that we've got to see, again, with our hypotheses test. The question is, assuming that these populations all have equal mean values, what's the likelihood of obtaining the data that we've obtained? And if it's very, very different than what we would expect, then we say, well, looks like there may be differences in the representative populations. If they're all sort of within what we would expect just based on sampling error, we would say, well, we don't have a strong evidence. We're not saying, remember that we're never saying with a null test that everything's the same, right? What we are saying is that we don't have enough evidence to say that there is differences. Based on the data that we've collected, there's not a sufficient amount of evidence to make strong claims that these are likely different. We're not saying they're the same, we just don't have enough evidence to say that they're different. Okay, that is a quick overview of our means-based tests. Do you have any questions about that? Okay, so at this point, right, we've been mostly focused on some univariate methods here, right, with some problems with univariate statistics, right? As we start to get into more advanced theories, as we start to get into more nuanced questions, we may start to become concerned that just relying on these univariate tests, these group-based statistics, starts to become cumbersome and inefficient, right? It leaves us a little bit lacking. So if I'm interested in the relation between gender and college performance, right? If I'm talking about college performance, what types of things go into college performance? Lots of things go into college performance, right? We look at course load, how many courses people are taking, how often they attend class, hours studied, GPA, how much people are invested, how much they are enjoying their experience, right? So tomorrow in Cynthia's lab, right, these are starting to become important for looking at kids with who have symptoms of ADHD or not, right? But if I want to go through and I want to look at differences in university students with ADHD and who don't have ADHD in terms of these things, that's a lot of t-tests to run, right? And so it starts to limit the types of questions that we can ask, right? I can say, what's the relation between trauma severity and psychological distress, right? What are we talking about here? Univariate. What might, assuming that this is continuous and that's continuous, how might we test that?
Simple regression.
What's that?
Simple regression.
Simple regression or correlation, right? One of those two things, right? Do men and women differ in levels of post-traumatic stress? What might we use there? Does that sound like? Yeah.
Independent sample t-test.
Independent sample t-test, right? Social support, post-traumatic severity, and other correlation types of things, right? But we're kind of limited in the types of questions we can ask, right? It's like, what is the relation between X and Y? Okay. So, if this is our concerns, we have a solution. It's going to be our multivariate statistics. Okay. Now, as we start to go through and look at our multivariate techniques, if we're talking about multivariate statistics in general, right? Broad class of techniques used to look at relations among different sets of variables, okay? So with our multivariate statistics, what we can start to do is fold in multiple predictors and also multiple outcomes depending on what types of models we're using. So one, we can start to include more variables in, right? Anybody point me in the direction of any psychological phenomenon that's based on two variables? No, people way more involved than that, right? There's a lot more going on. So we want to have models that start to incorporate multiple different factors. Multivariate statistics allows us to do this. Our multivariate tests also can start to capitalize on different associations between variables that are included in our models. And this is nice because it starts to increase the power, right? So if I'm using a ANOVA model, in some cases a ANOVA is going to be more powerful test than a bunch of independent ANOVA models, right? So under certain circumstances, our multivariate tests can start to give us a little bit more power to test the things that we're wanting to look at. And probably the most important here, range and complexity of research questions that we can ask starts to increase, and that way our studies start to become better approximations, never perfect approximations of the real world, but it starts to get at more complex and more elegant types of designs, right? So if I say, what factors change the relation between trauma exposure and stress? So Ignacio, Sean, I do trauma and anxiety research, so that's the stuff that I have, so you'll become indirect experts at trauma and anxiety by the time you finish up the thing. But if this is my question, what factors change the relation between trauma exposure and distress? What type of question? Does anybody know what type of question we're asking here? Moderator.
One of them.
Right? Maybe one of them, whatever. Talking about a moderation question, right? I've got a relation between X and Y. What's a third variable that starts to change the nature of that relation? Strength and direction of that, right? And that starts to become interesting. We know X and Y are related, but are X and Y related for always and forever the same way under all circumstances and conditions? Probably not. There are probably things that start to change the strength of that relationship, right? And so this starts to become a more interesting question to get at some behavioral stuff, right? What factors account for the relation between trauma exposure and prolonged distress? Okay? We're talking about a mechanism, an action question. What type of test are we asking there? There we go, mediator. Sally, you're so much smarter than Chris. Right? Mediator, right? What are the things that account for X and Y are related? Why, right? What are the things that? Why are those two things? What's the causal mechanism going on with this, right? And if we ask about talking about unique contributions of various risk factors to the occurrence of PTSD, right? So we know that only a small percentage of people who are exposed to trauma actually develop chronic symptoms, right? So we might be interested in what are the factors, what are the risk factors that start to increase the likelihood of developing symptoms, right? But is it probably just one thing? No, probably a whole host of things, right? There's a lot of overlap. So what types of model or question or technique might we use to answer this last question?
Interaction effects?
What's that?
Interaction effects?
Well, interaction effects that's going to be a moderation question, but here just a straight regression, right? Here, if we have a multiple regression model and we've got, say, 4 or 5 different predictors, 4 or 5 different risk factors, we can start to see, so let's say we have respondent sex and trauma history, like cumulative trauma history, right? And we find that that women are at high risk for developing chronic symptoms, right? But when we throw trauma history in there, we might find that women are actually at greater risk for victimization, and so I have larger trauma histories. And once you account for that, sex doesn't predict anything, right? And so what we're looking at here is a unique contribution that we can start to sort of tease out above and beyond sort of X, what's the contribution and the prediction of some outcome here with just a multiple regression model, right? So we're starting to get in much more nuanced and interesting questions with our multivariate statistics than we were able to get at with our bivariate tests. So how do we keep all these organized? There's a lot of different stuff, right? Here is where your GLM comes in, okay? Again, your GLM, just a broad statistical model, a lot of different variations, a lot of different analyses here. GLM, this is like your basic internal combustion engine of statistics, right? This is why your Ferrari and your lawnmower at the end of the day are not dissimilar in terms of the basic things. It's the reason that I'm sort of not different than a field mouse in terms of the cellular level is that the basic things are sort of going on to keep that alive, keep me alive, right? This is your GLM, okay? If you were familiar, you start to see the connections and sort of be able to make the connections with the GLM, it's going to help out organizing your analyses, right? So I'm doing this or that, it doesn't really matter. Sort of the underlying basic technique is the same, but if we're using different variables, different numbers, sort of recognizing this as the common underlying structure for a lot of the things we do can be helpful. Helping select models, and then if you have a good handle on this, can help you be more proficient as you start to get farther along into doing sort of more complex types of analyses. What happens in applied statistics and research oftentimes is people running with scissors, right? Particularly with at one point in our time, and to run anything like a basic regression model or something like that, if you had to run your regression model by hand, people who didn't know how to run regression models weren't running regression models because you had to do it all by hand or punch cards on a mainframe or something along those lines, right? The advent of statistical packages, really, really nice. It makes these analyses much more accessible, right? But at the end of the day, with pull down menus, if I can just point and click, it's going to give me something, right? But if I don't understand what it should look like and whether or not my results are meaningful or whether or not I'm doing it correctly, right? Think about this. You wouldn't want your heart surgeon to be like, well, I read through the steps, and if I follow these steps, I should be able to, everything should be fine. I don't know so much about biology or physiology, but I know if I cut here and do this, we'll probably be okay, right? A little less dire consequences with statistics. No one's going to have heart failure or crash on the operating table because you screwed up your regression analyses, but it's basically the same. Okay, so general assumptions of your general linear model. First thing we need to think about, and this is starting to become important, is in terms of thinking about linearity. Okay, linearity assumptions. We're assuming that within our GLM, pairs of different variables are going to hold a linear relationship. Okay, here we're saying that the association between any two variables in my model should be adequately represented by a straight line. Okay, and if I start to violate this, what ends up happening is I can start to, my estimates of association start to become smaller than they should be, right? And in some cases, I can get spurious effects or fail to detect relationships that are actually there, right? We can have situations where X is associated with Y. It's just X is associated with Y in a nonlinear fashion. So because of that, I miss it, right? So for example, we go through Alicia. We've got correlation between husband's age and wife's age. Is this adequately represented by a straight line? Yeah, right? You've got a clear linear path, right? The association here, if you tried to fit anything else other than a straight line to that, I think you'd probably be off the mark, right? Tomorrow, what about this? We got, I know you're a motorhead, so we got the ratio of horsepower to drive ratio here. Does this look like it's best represented with a straight line?
Probably not.
What's that?
Probably not.
Probably not. What do you think fits better than this, than a straight line?
I don't know what it's called.
A quadratic or curvilinear? Maybe, right? Maybe. I don't know though. I would go through and I'd say like it's not. Is a straight line perfect? Probably. Well, probably not. Definitely not. Right. But I don't know. I might put my money on a straight line here. Maybe right that we could get sort of a decreasing function there, but probably in terms of parsimony, a straight line probably not bad, right? At least at the very least, and we could go through and test this, right? But at the very least, I wouldn't look at that scatter plot and say, a linear model is inappropriate for that. It's not going to be as good as that, right? But it's still probably not going to be, it's not grossly inadequate, probably. But what about this? How about this? So we've got fit for that. Probably not. Why not?
It's kind of like flat.
What's that?
It's like flat, kind of.
It's
Not-
flat. Did you use the word parabola? Or did I just hear that, Mike? Because I was going to give you a high five. Or you
Yeah, I used it.
Were you going to say something, Chris?
I just thought it looked like a boat. Sorry.
It looks like a ski, right? Yeah, probably some sort of nonlinear function. There's probably a growth function here, right? Where could I fit a line to that? Yeah, I could fit a line to that, right? And a line might actually be, in terms of parsimony, a reasonably good fit, right? But it's probably not this. So it looks like we've got maybe some sort of exponential function going on here. And so my general linear model is probably not going to totally miss this relationship. It's going to say, yeah, there is an association between education and income, but that association might be weaker, that I estimate, with a straight line might be weaker than the actual association between these two variables if I were to actually fit a line here, okay? What about this?
You draw a bunch of lines.
So relations.
What do you think? CJ, is a linear model a reasonable way to represent those data?
Nope.
Why not?
Kind of scattered everywhere.
Kind of scattered. What model would you prefer? Is there a better model than a straight line?
Just transform it. Probably you will find something.
Maybe if we transform it, right? These are just uncorrelated data, right? And so while a line is not a good fit for that because it's just a big cloud, it's also probably not an inappropriate model for that. Basically what we have is just two variables that have no relation to one another, right? And so really, in this situation, it's not that we've chosen the wrong model, it's just that there's no association to be found there, right? What if, though, Laura, would you mind, I forgot the markers.
Josh, I have some if you want.
What's that?
I have a few if you
Oh,
want.
do you? Awesome, cool, yeah. It is. Sean's the big winner, coming in, new guy, saving the day.
I'm teaching this semester.
What if we've got okay, so the difference between this and this, okay, is a linear model an adequate representation of that? If I try and represent this, the relation between x and y with a linear function, what is that linear function going to look like?
It's a normal solution.
Zero slope probably.
Zero slope, right? It's just going to be flat. And if I test that, what's it going to say the association between x and y is? 0, right? Is there no relation between x and y? Well, there's a very strong relation between x and y, right? We just missed it with the linear model, right? And what we've said, and if we're looking just on our output, this is also another important reason, why screening is important, right? Because if I haven't gone through and looked at my data graphically, and I look at the relation between x and y, I say these two things aren't related to one another, right? When in fact they very much are. It's just not something that's adequately represented with a straight line, right? Now this is a different scenario than this, right? Here, I don't know, I think actually probably your straight line is probably your best bet with that, right? It's going to be the simplest model that tells you that there's nothing there going on, right? And so now, so if we have questions about maybe there's some transformations or things like that, we could probably, but here is just a cloud, probably not much going on, right? So we want to make sure, and so when we're going through and running screens and things like that, part of this is taking an assessment of this linearity assumption to make sure that if we're trying to fit a linear model to our data, that a linear model is actually appropriate and is actually going to be a reasonable fit, right? So again, but things like this, I can fit a linear model of that. But then what I might want to do is then maybe fit an exponential model, a quadratic model. And what I want to do is see how much more, what's the benefit, what's the incremental benefit, how much of the total variability in my outcome am I getting by fitting the more complex model than the linear model? And if it's quite a bit, if the fit of that model increases by quite a large degree, then I'd say, oh, I'm going to use a more complex model. If not, if it's, you know, maybe an additional 0.5% of the variability, I might say, well, looks like maybe a curvilinear model might be a better fit, but for the purposes of just representing these data, the simpler model is probably going to be the better bet, just each moving forward, right? But all of this is stuff that we'll go through and do in terms of screening and looking at our data. Okay? So questions about linearity assumptions. Okay. Other model assumption of our generalized linear model is going to be an additivity assumption. What we're saying here is that as we include additional predictors, these are going to contribute incrementally to the prediction of variability in my outcome, right? So I've got my first predictor in my regression model, right? And then I'm going to add a second predictor that adds things above and beyond the stuff that the first predictor did, right? There's stuff in my outcome, there's variability in my outcome that wasn't captured by the first predictor that's being captured by the second predictor. And if I add a third predictor, this predictor is capturing a different piece of the pie than the other two, right? So if we're thinking about total variability in Y here, right? This is all the stuff that I want to predict with my model, right? My first predictor gets this, right? But then, Chris, where do I want my second predictor? Where do I want that to fall in this whole thing?
Somewhere not touching.
Yeah, right? Like something that's not exactly overlapping with that, because then I don't have an efficient model, right? I basically included X1 twice and just called it something different, right? So best case scenario, X2 is coming up over here, right? And X3 getting something here. And then maybe X4, some overlap with these two, right? But really kind of getting at a big chunk of new stuff. And so in psychology, we often don't do this, right? Particularly in clinical psychology, where all our measures are saturated with negative affectivity, and we just throw in 5 negative affect measures all at the same time, and then get real sad when nothing turns out, right? Well, that's because all my predictors are all like this on top of one another, right? With our linear model, if we've got a good, efficient model, best case scenario is that all of our predictors would be orthogonal to one another, right? All our X's are uncorrelated with one another. That's going to be our most efficient model. Now, in actual fact, particularly when we're looking at a lot of psychological stuff, everything's related to everything, so it's impossible, it's not reasonable to expect all of your predictors to be uncorrelated with one another. But as we're going through and doing something, we certainly don't want our predictor variables to be correlated 0.7, 0.8 with one another, because then we're just basically, there's too much redundancy. We get into problems with multiclinearity, increase in sort of inflating our standard errors and a bunch of other stuff, right? So this starts to become important as we're planning studies and experiments, and we'll talk about this, how having good predictors that account for a lot of your outcome, but aren't hugely overlapping with one another, adds tremendous amounts of power to your analyses, right? But you have to be thoughtful about this, because if you just pull into the grab bag of, oh, these are the variables that we have, you're probably going to get a lot of stuff that's redundant with one another, and then that's not always so helpful. All right. So what does our GLM look like? GLM looks like, but fortunately for us, we're not econ folks or marketing folks, and so we're not going to worry about this, right? We're going to accept that that's a true statement that other people who are big on mathematics have figured out. So we'll leave that there, and we're going to focus more on just basic linear functions, right? So if I go through and I say, what's the relation of depression to post-trauma symptoms in community survivors with PTSD? Okay. How many predictors do I have in this model? 2. Well,
One.
yeah, 2 three variables, one predictor, one outcome, right? And in this case, we'll say well, does it matter which one's the predictor and which one's the outcome? No, right? It's correlational, you can flop one. It's basically going to be a conceptual issue. Which one am I thinking is the thing that's associated with the other thing, right? But if we go through and use our simple regression model, all right, y hat, this is going to be our expected value of y. Not the real value of y, but the value of y that's predicted by our model, right? So we've got our expected value of y equals a plus bx. And if we actually run this out and we run these data, we find that our regression equation, so y hat, or expected value of y, is equal to 24.8 plus 1x. So, if this is my equation, Nick, what's my expected value of PTSD? If PTSD is y, depression is x, what's my expected value of PTSD when depression is equal to 0? 24, that's friggin' brilliant. How did you know that? Algebra, exactly. Okay, this is one of these things, as we start to get into this, right? Like, particularly as psych majors, sometimes we want to just like sort of eyes glaze over if I see an equation. Don't. That contains an incredible amount of information about what's actually going on, right? So if depression is x, PTSD is y, and I say, if the question is, what's the expected value of PTSD when depression is equal to 0? Put 0 there, that goes away, and I'm just left with 24.8, right? I think oftentimes we want to just look at p-values and stuff that don't, like, particularly as we start to get into moderation, you're going to need to be able to be comfortable and start to manipulate these equations, right? Again, this is a different thing when we've got on like econ or marketing types of committees, right? Question is, so what's the equation, right? A lot of econ papers, like there's the literal regression equation is sort of listed out there as evidence that so we've gone through and done stuff. We don't do that in psychology, but it's a good way to kind of know what's going on with stuff, right? And as we start to go into, manipulating things with moderation questions, you're going to have to be able to work with these linear models and sort of see what happens if I move things around. If you're able to do that and you're comfortable with that, it's going to make a ton more sense than just trying to memorize what happens if I sort of start switching things around. Okay? So, someone else, Sean, I'll pick on you. What's the expected change in PTSD given a unit change in depression? 1, right? How did you know that?
It's the slope of the x.
Yeah, it's my slope, it's my coefficient, right? We're seeing every time I increase my depression score, I'm expecting my PTSD score to increase by 1 unit. Right? So a unit change in depression based on my model is going to result in a unit change in my outcome, right? Expected change in my outcome. Now, whether or not that actually really corresponds, we're going to have some error in the model, but based on my equation, I would expect for every 4 unit increase in depression, we can get a unit increase in PTSD. Okay? And so if we look at this, this is what a scatter plot looks like. If we go through and we draw our regression line, this is what we get, right? Alicia, is a linear model appropriate for these data? Yeah, right? Is it a perfect model? Not perfect, right? But it does a reasonable job of representing the association between depression and PTSD. I don't know that there's a different model that's going to do a better job than this, right? Probably what we would need to do is have a lot more things. If I don't want to predict post-traumatic stress disorder, there's probably other things I need to be considering outside of just depression scores. That's going to start to suck up some of the additional variability going on there. Questions about sort of how we're utilizing this? Okay. Other thing we have, so this here, these, what we've got here is what we normally call an unstandardized solution. Okay? An unstandardized solution has a lot of utility, particularly if we're in situations, again, keep going back to you guys, a lot of times in marketing, right? If I'm a marketing researcher, what's oftentimes my outcome that I'm interested in?
Revenue.
Yeah, profit, dollars, right? And if I tell you, if I spend X number of dollars to get this number of profit, that's something we all understand, right? So that coefficient actually means something, right? For every increased dollar that I spend on marketing, I get $5 in terms of additional revenue profit, right? That makes some sense, right? And so when we're working with variables that have, or Chris, like the stuff that you guys do, right? Like if weight, you know, sort of body mass is some sort of outcome, right? And so we're looking at like hours spent exercising versus body mass and things like that. Hours of exercise is something that I understand, right? Weight, mass is something that I understand. So these unstandardized coefficients and then these unstandardized models can communicate a lot of information, right? But if, let's say you're me, right? And I'm looking at trauma symptom or anxiety and sort of affective expressivity or something like that built on a self-report scale, right? Whatever number that is, 0 to 50, number of general expressivity, that doesn't mean anything. I don't know what it is. A 5-unit increase big? Is it small? I don't know, right? In these situations, standardized models can start to become effective or sort of communicate important information. With our standardized models, what we're going to do here is we're going to convert all our X values and all our Y values to Z-scores. Okay? And what this is going to do is it's not going to put X and Y on a common scale, right? And the point at which my regression line intersects is going to be where both of these variables are equal to 0. Okay? Now, for a standardized score, if I'm talking about Z-scores, deciding what does 0 mean? If I say someone has a Z-score of 0, what does that mean?
It's the center of the normal distribution.
Exactly. This person has a score that lies at the average of sort of whatever the sample is, right? And so what we've got with our standardized scores, not different than what we had before, we can start to see that my regression line starts to intersect right here where both of these are the mean of both values. Same thing happened with the unstandardized. We can just see it, right? So 0, 0. So this point right here, my regression line has to go through that score, right? Or that point on the graph. Impacts on the model. What I'll end up with my standardized equation. I have my expected value of y equals my standardized coefficient times whatever my variable is, right? Here, we just have y hat equals 0.535x. Chrissy, what did we lose in this equation?
A.
Mm-hmm. A's gone, y's A gone.
Which is,
It's there, it's just 0.
It's 0, yeah.
Yeah,
I would agree with that.
Yeah, it's gone, right? So the expected value of
when it's
y,
zero,
yeah, expected value of y when x is 0 is 0, so it just goes away. We don't need it anymore, right? And so what we see with our standardized models, that intercept goes away because it's just 0, right? But our interpretation of this coefficient changes, right? So before, we were interpreting our coefficient as the expected unit change in y given a unit change in x, right? The idea doesn't change. With our standardized models, my coefficient is still an expected unit change in y given a unit change in x, except now with our standardized model, what are our units?
Standard deviation.
Standard deviations, because we're using Z-scores, right? So what we would say, how I would interpret this is I would say a standard deviation increase in repression is expected to produce about a half standard deviation increase in PTSD scores, right? So the form doesn't change. It's just what we're using as the unit starts to change, right? So thinking about this, and this starts to become important, or will start to become more important when we think about, so in 50-60, we talked a lot about not just sort of saying, is this association between x and y 0, right? Tomorrow, what else were we interested in sort of talking about in terms of our interpretations? Effect size and sort of in addition to that, confidence, yeah, and so what if something's not zero, we start to get in with regression models, is if I'm using some measure that ranges from 0 to 100, right, and I'm sort of looking at the association with some other thing that is on a 0 to 100 scale, right, and I have, let's say, y hat equals 25 plus 0.5x, right? And so so b equals 0.5, and that's p equals 0.608, okay? So we have, based on our data, right, we know that a unit change in x is associated with a half unit change in y, right? And we know that based on the data that we've collected, that these data are relatively unlikely, assuming that the population coefficient for b here is 0, right? But our question starts to be, is that a meaningful difference? Like, is there a meaningful association between these two? And it's kind of hard, right? Because I don't know anything about x and y, right? You got a unit change in a 0 to 100 scale isn't much of a shift, right? So is this important? Is this not important? I don't know, right? What we can start to do is we can start to think about using our standardized effects here. And so if our standardized coefficient here is b equals, let's say 0.40, okay. CJ, what's my interpretation of this coefficient? If this is a standardized coefficient, yeah.
With each standard deviation change, you would expect the other variables to change by a factor of 0.4.
Yeah, perfect, right? For every standard deviation increase I get in my predictor, I'm getting about 0.4 of a standard deviation increase in my outcome, right? That's pretty sizable, right? And the problem is when we're thinking about in terms of practical impact, right? It's sometimes hard given the original scale of our predictors, because a 1 unit change, our regression model is always going to tell us to the expected change in y given a unit change in x. But a unit change in x might not be anything that's reasonable or interesting for me, right? And so what our standardized models or standardized solutions start to do is put things on a common metric. And so I understand in general what a standard deviation change is. That's quite a bit, right? And so it starts to help me gauge a little bit better practical implications for sort of my research and sort of do a better job of tying more meaning. It's a little bit harder with this, right? Because with our group-based models, well, we've got this group and that group, and so this is the difference. And if it's a 1/10 of a point on a 50-point scale, I can say, well, it's not 0, but it's probably not something that we should get too overly worked up about, right? Harder to do with this stuff, but our standardized models can start to help gauge, in addition to understanding sort of the field and things along those lines. Yeah.
In this model, what is the practical difference between the coefficient and what we talked about as the effect size?
We'll get into that. Your standardized coefficient is a rough version of an effect size, right? And so this is something now, there's not clear benchmarks for what is a sort of large, small, medium, large, beta. There's other statistics that we use. They're very similar, sort of semi-redundant with that, but we'll get into that when we get into regression. Questions about this? All right, cool. Okay, so if we're thinking about the bivariate case, right? Bivariate case, we've got one predictor, one outcome. Our bivariate GLM, 3 specialized forms of analyses here. So in the case where our x is continuous and our y is continuous, talking about a Pearson correlation. Okay. We can also run a regression model with that. So our standardized coefficient for our regression models is the same as our correlation coefficient, right? But if we've got continuous x, continuous y, probably talking about a Pearson correlation. If However, my predictor is dichotomous, right? So 1 or 2, it's a categorical variable, take 0, 1, my outcome is continuous. Got a couple different things. This technically we would call point by serial correlation. In actual fact is functionally the same thing as our Pearson correlation, but we can also think about this as a t-test, right? Either these two things are interchangeable. The only thing that makes a difference is how you want to talk about it. Do I want to talk about things in terms of the relation between gender and neuroticism, or do I want to talk about this in terms of average differences across men and women? Statistically, it makes no difference. They're exactly the same. But for communicating things, it can certainly become important. Other option is we have our X is dichotomous, our Y is dichotomous. Here, again, P coefficient. This is, again, functionally identical to a Pearson correlation. Or we can talk about this as a chi-square test of independence. Is our X and Y related to one another, right? Now this is, again, holds only in the 2 by 2 case, right? So we've got a dichotomous X, a dichotomous Y, but again, interchangeable in terms of how you talk about these things.
Do you refer to Spearman correlation with 5 coefficient?
We'll get into that. We'll get into Spearman and some of those other options. We actually don't see a lot of different variations on what ends up happening in psychology. Everybody stuffs everything into a Pearson, even if that's not 100% appropriate. But we'll go through at the end of the correlation lecture to present sort of some different coefficients that are probably more appropriate depending on your level of measurement. All right. Questions about this? Okay. Take home here is that a point by serial correlation, a t-test, no different, right? They look different, right? And it will be maybe different how we talk about them, but from the purpose of a GLM, they're both sort of different versions of the GLM, they're identical. Same thing with the P coefficient with chi-square, same thing, right? It doesn't matter. I've had co-authors be like, oh, just give me a correlation between sex and whatever outcome it is we're looking at. They're like, oh, you can't do that. That's not appropriate. Like, it's the same. It's mathematically the same. It doesn't make a difference. You can fight with people about because someone learned in a class like, oh, you have to do it this way. You don't. It's a free country we live in. Like, as long as it's sort of not sort of a violation, it's like we can talk about it however we want to talk about it. Okay. All right. So again, functional equivalent analyses. The only thing that's going on here different than the types of stuff that we've done in the 50-60, we're talking about means-based analyses, right? Like this group is different than that group by sort of this number of average units across things, right? And that's perfectly fine, and probably the way we should talk about a lot of experimental designs and group-based analyses, right? But we don't have to. We can talk about things in terms of relations between our continuous outcome, our group variables, and things along those lines. Either one of those is fair game. Questions about this? All right. So thinking about this, like, so why we've got these group-based analyses, we've got t-tests, we've got ANOVAs and things like that, right? Let's say I'm looking at, Nick is doing this. Nick's looking at a study where looking at the differences in alcohol consumption across class standing, right? So we've got freshmen, sophomores, juniors, seniors, right? And Nick is interested in differences in number of alcoholic drinks per week, month? Okay, let's say month. Number of alcoholic drinks a month across these 4 different groups, right? What's one option for Nick to use in terms of looking at those data? What probably makes the most sense? Yeah, one way I know, right? We've got how many independent variables do we have? There you go. Oh, I'm so smart. 1, right? Class standing, 4 levels: freshman, sophomore, junior, senior, right? And now probably what makes sense is just to go through, look at this with a one-way ANOVA, right? And then we can talk about mean differences across different groups, right? But do we have to look at it that way? We just got one independent variable and one dependent variable, right? We could, modeled appropriately, talk about this as the relation between class standing and alcohol use, right? That's perfectly fine to talk about it that way if we wanted to, it starts to get complicated to sort of capture that in one number. ANOVA is probably the best way to go in terms of communication. But we could also think about this as a GLM problem where we've got it looking at the relation between a categorical variable and a continuous outcome, okay? What's nice in terms of thinking about this is we can start to take that model and then start to layer on and start to add more variables and think about things a little bit more flexibly than just saying, are there mean differences across groups? Or we can start to layer in other types of variables and things like that to sort of fill this out, right? And so what we can do here is we can take our simple generalized linear model and taking that bivariate form, start to include multiple predictors, right? So I've still got one y. What I want to do is I want to add more predictors. So in addition to class standing, I want to add some other things in there to start to predict variability in number of drinks per month. Nick, what are the types of things, if I'm trying to predict number of drinks per month in college students, what other variables might I want to consider?
Greek life.
Greek life, okay. So am I involved in Greek life? That's a big thing. What else?
Other reported substance use, first time.
Okay, so history of substance use, things like that. You got anything else?
Just age.
Age.
If they're legal for drink.
No, that's a good question, because age is going to be to some degree correlated with class standing, but not perfectly, right? So I have non-traditional students or people who are sort of older, so that might start to suck up variability that's sort of hanging out in my error term, right? What I can do with my multivariate GLM is I can start to incorporate not just class standing, but a number of different variables to start to predict my outcome here, right? And in this case, what we're expecting is that our outcome, our predicted value of our outcome, we're gonna use the weighted sum of my relative predictors, and we're going to look at that, right? So in this case, I'm going to say class standing is going to predict some level of my outcome, right? And then in addition to that, I'm going to add in Greek life, and that's going to capture some additional stuff that class standing didn't capture. And then I'm going to add in history of prior alcohol use or substance use, and I'm going to include age, right? And the idea is that each one of these hopefully should start to pick up pieces and parts of this that the other ones didn't, okay? So if I go through and I ask, what's the unique association of depression, trait anxiety, and social support with PTSD scores in survivors of traumatic accidents, right? What I've got here in my standardized form is I've got my standardized outcome, and then I've got a coefficient for depression that represents the unique association of depression with PTSD, and then for my anxiety score of PTSD, and then social support here. Chris.
Yep.
You
faked me out.
To be the head fake, or you didn't see. What are you seeing in terms of anything that you're noticing in terms of these coefficients?
It looks like social support is negatively associated.
Okay, cool. And what does that mean?
The more social support you have, the less.
Beautiful. Okay. And how does that relate to these other two?
The other two, the more you have, they're positively associated with PTSD, so the more you have, the more PTSD.
Cool. Nice. And if this is a standardized score, which one of these was the biggest predictor of PTSD? Depression, right? Again, because in my standardized solution, we put everything on the same scale, right? And now I don't know if there's a meaningful difference, right? Or is it sort of more than just general variation? But this is looking quite a bit bigger than these other two, right? But the idea is that when I'm predicting my outcome here, at least within this model, my depression score, that's getting the biggest chunk, right? But then anxiety is counting for a little bit more, social support accounting for a little bit more. My ultimate score on that I'm predicting for my outcome is going to be the sum of sort of the weighted scores of each one of my predictors. So the important thing to recognize is that once we transition to our multivariate GLM, these coefficients here these no longer represent a direct correlation between my predictor and my outcome, okay? They can, as long as my predictors are uncorrelated with one another, right? But you notice it talking about the unique association with depression, trait anxiety, and social support with my outcome. That's because are depression, trait anxiety, and social support going to be uncorrelated with one another? Alicia? Absolutely not. They're all going to be correlated, all sitting on top of one another, right? And so anything that's overlapping isn't getting any credit for this. That's just going into your R squared. We'll get into that down the road, right? But in terms of our multivariate GLM, what we're looking at, we'll talk about these as partial coefficients, right? This is the unique part of depression that's independent of anxiety and social support that's holding an association with my outcome. And this is the unique proportion of trait anxiety after we account for shared stuff with depression and social support that's associated with the outcome. Yeah. That's it.
The primitive question. Trait anxiety is the same as anxiety?
Yeah. Trait anxiety, same as anxiety. And thank you. Yeah. We're just going to use a lot of psychology terms and things like that. You don't have to have special knowledge of psychology terms, but if stuff comes up, feel free to ask that, right? So, tomorrow, the thing about so this looks like a pretty minimal association between trait anxiety and PTSD. I know you're not a trauma person, but if we just looked at the correlation between trait anxiety and PTSD, what do you think that correlation is probably going to be? Big or small? Really big, right? But we notice that this is really small, right? Why is that?
Because the overlap.
Yeah, because there's a huge amount of overlap. So we know depression and anxiety are hugely overlapped with one another. Many people will argue that they're functionally indistinguishable in terms of self-report measures and things like that, right? But in this model, so if I were to just look at the bivariate correlation between trait anxiety and PTSD, it would probably be quite large. But as soon as I start to section out all the other stuff that's shared with depression and social support, now all of a sudden the stuff that's remaining, it's pretty small, right? And so in psychology, so the stuff that we do, these regression models are really nice to say, so what is the unique contribution of this variable to predicting something above and beyond sort of shared stuff with whatever other variables we have on. Okay? And so we'll talk about this as being these in terms of partial coefficients is a really important part of thinking about how we interpret things. All right. So a simple multivariate GLM, right? This is going to be a bunch of x's, one y, right? If I have a number of continuous x variables and a continuous y variable, I'm talking about a regression model. If I have my x variable is discrete, right, and my outcome is continuous. We're talking about an ANOVA model here, right? I've got one or two different variables, and so this would probably be better represented as a factorial ANOVA, right? And we talked about these last semester. I've got CJ's looking at motivation stuff and has this thesis he's got planned out, so he's going to do groundbreaking, right? You got a couple of experimental conditions, right, that are crossed. So you got two experimental conditions. You got condition A, condition B, or condition 1, manipulation 2, and then a continuous outcome, right? You've got multiple discrete IVs. This is going to be an ANOVA model here, okay? If I have a mixture of continuous and categorical, or just a mixture of continuous and categorical independent variables and a continuous outcome, probably looking at an ANOVA model, okay? So this is sort of mixing up things a little bit. If I have a continuous outcome of categorical, or continuous predictors, categorical outcome, talking about discriminant function analyses. We don't see too many DFAs in psych science these days. They used to be on trend in the 90s. No one really does them much anymore. We've got better models than that, but that's on there. If we've got a mixture of continuous and categorical predictors and a categorical outcome, here we're talking about a logistic regression. if we've got a mixture of continuous and categorical outcomes, and our outcome, or mixture of continuous and categorical IVs, and my outcome is some time to an event, right? How long before this? The predictors are some mixture of time and continuous and categorical variables, and I have a continuous outcome. We'll do some time series analyses, right? We don't do a lot of time series analyses. I took a workshop in Ann Arbor on time series analyses, and I've never used it again because I don't know. The stuff that we do in psychological science doesn't lend itself well to time series analyses except for specific examples, but econ and a lot of time series analyses starts to become relevant, right? So, but the thing is if we start to understand sort of the relationships between some of these, if I just, again, I say, okay, here are my predictors, here's the level of measurement, here's the outcome or outcomes that I have, this will very, very quickly start to narrow down the types of analyses that are appropriate to answer your question. All right, so limitations up to this point. A lot of the same stuff gripes we had about our bivariate analyses, we would say the same thing about our simple multivariate model, right? Well, I've got, these are cumbersome and inefficient if I have a number of different outcomes that I'm interested in, right? It's also limiting the types of analyses or the types of associations that I might be interested in taking a look at, right? The thing is, like, what if I have not just one outcome, but I have multiple outcomes? What about that? What if I want to look at that, right? Let's say we're going back, what's the relation between gender and college performance, right? Because Tamara's doing this study. She's interested in looking at, let's not say gender, let's say ADHD, right? ADHD diagnoses and college performance. Well, college performance isn't just one thing, it's a multifaceted construct. We can talk about college performance. There's a number of different ways we can operationalize that. There's a number of different components, right? And so I'm interested in course load, attendance, hours, GPA, major GPA, investment liking, things along those lines. That's a lot of different models if I've got 5 different outcomes I want to take a look at, right? What we can do is we can take those and transition into a full multivariate GLM. Or full multivariate GLM, right? So people will start to say, you'll hear different terminology. People will talk about like multiple regression. Standard multiple regression is not being a multivariate analysis. Well, it's got more than one IV, right? So technically, we'd say simple multivariate form. Full multivariate form is going to be multiple IVs, multiple PVs. Okay. So here we've got a number. We've got 1, 2, 3, sort of however many outcome variables. We've got 1, 2, 3, however many IVs, right? And we're going to look at these all in the same model. Okay. Now, from a mathematical issue, sort of thinking about interpretations, what we need to do is start to recognize that we often need to, with our simple multivariate model, we just had one regression equation, right? One regression equation did a fine job of capturing the unique associations between our predictors and our outcome. If I have more than one outcome, I often need more than one equation to start to adequately capture the relation between all of my x's and all of my y's. So think about if I have sort of different types of algebra, I got multiple unknowns, right? If I just have one unknown in my equation, it's pretty easy, straightforward to figure out, right? But remember back to like in high school when you did that, all of a sudden now we've got x's and y's all in the same thing. All of a sudden now this mind blowing. It's hard. Here, if I'm just looking at Ignacio, if I have x plus y equals 24, can you tell me what x and y is definitively?
What do you have?
Yeah, so I just say,
It's a combination of
What's that?
whatever is add ups to 24.
Right. Well, and so if I have x and y, and this is all we have, there's an infinite number of solutions that I could have for that. Like I don't have a unique solution for that. And if I don't have a unique solution, then it's not super useful for me. Like, I don't know, make up whatever you want to do it, right? We got 1 degree of freedom here. As soon as I choose x, then y is determined, but there's no unique solution that I can agree on, right? But if I start to get, in addition to this, then I give you the second equation. Well, x plus y equals 24, but also 2x minus y equals -6. Can I solve that now? Now all of a sudden we've got a solution here, right? And so this is kind of how our full multivariate model works. We need to have oftentimes we need to have multiple equations in order to account for all the combined relations between our variables that we're working with. Okay? Now, this linear combination in our full multivariate, depending on what type of analysis you're using, you'll hear these equations called use different terms. Characteristic roots, DFA, optimal, we're going to talk about characteristic roots. If we're doing factor analysis, we're talking about principal components, right? It's the same thing. There's just a series of linear equations that are capturing the relations between this set of variables, okay? And when we're doing this type of stuff, what we find is there's generally as many roots or linear equations as the smallest number of my x and y variables, okay? So let's say Siley's running a study, and she has 5 IVs and 3 DVs, right? There are, in this situation, sort of the max number of roots, there are probably 3 roots here, 3 linear equations that could be used to capture the relation between those variables, right? So we got 5 IVs, 3 DVs. Number of roots is the smallest number of x and y variables. So we got 3 there, so we got 3 roots, okay? So that's the max number, but we don't necessarily need 3 linear equations to capture that. Sometimes we can do it with less, but 3 is going to be the most. Okay. So let's say I'm looking at the association between a number of predictors. Let's say I've got 10 predictors, 10 IDs, right? In predicting 2 outcome variables, I'm trying to predict self-esteem and extroversion. Okay. And if I go through and I look at here's my sort of level of self-esteem and here's my level of extroversion, right? I might be able to capture the distinction between sort of these things with one root, right? So the sum of my weighted predictors is going to help me differentiate between scores on self-esteem and extroversion here, right? This one's here along the dimension, this one's here along the dimension, cool, those things are separated out. Okay? But let's say I add a third variable here. Let's say I add social desirability into the mix. And social desirability ends up here. Okay? Is my one root sufficient to distinguish between sort of all of these variables in 2-dimensional space? Why not, Nick?
Because doesn't fit in that relationship.
Yeah, specifically, sort of like, and this is kind of a hard thing to wrap your head around without sort of shifting into multi-dimensional space in your brain. But you had said, you know, sort of, yeah, the ideas on why that one root is not sufficient. Yeah, what is the third outcome conflated with here? On my root, on my linear equation, where does social desirability exist? It exists in the same spot as what? Yeah, these things, right? If I'm sort of coming along, this is my characteristic, this is my equation, right? And I'm traveling along, and I had self-esteem, cool. Travel along, and then I hit here. Am I able to distinguish between extroversion and social desirability? No, because they exist in the same spot, right? But what I can do is I can add a second characteristic root. Okay. Now on my first root, right, I've separated self-esteem separate from social desirability and extroversion, right? I can do that, but with my first root, I can't distinguish between social desirability and extroversion, right? Chris, where do I go? What is my second root help me do?
Understand where, I forgot what SD stands for, but
Social desirability.
Social desirability exists within that plan.
It captures this up here, right? What is my second root not capable of distinguishing between?
Understanding where extroversion exists on the plan.
Relative to self-esteem, right? Because on my second root, self-esteem and extroversion exist in the same spot, right? But it helps me differentiate these two. And so with these two equations, I can go through and capture where all three of these, my outcome variables are, whereas I can't do that with just the one. Sean, what if the location of social desirability changes in my sort of equation? And what if social desirability isn't here? What if it's right there? Do I need a second root?
Probably just use root
No,
one.
just. There we go. Yeah, now we just need the one root, right? And so recognizing that within these full multivariate models, we don't always need the max amount of characteristic roots, right? This would be like, let's say I'm running a factor analysis. If I run a factor analysis with 20 indicators, how many characteristic roots do I have? 20, right? Is a 20 factor solution for 20 items, is that a useful thing? No, that's not a useful thing. The idea is that we hope to get, be able to account for the interrelation between these variables with a fewer number of dimensions than is available in the data, right? And so recognizing that when we get into these fully multivariate models, things start to get a little more complex, and thinking about like with any statistical model is a simplification of reality, right? No statistical model is intended to be an exact replication of what actually happens, right? It's a way of reducing things to try and make something a little bit more simple, a simplified version of reality that allows us to make reasonable predictions about some likely outcome, right? And so, same thing with sort of our curvilinear function, right? Statistically, a curvilinear function might fit that incrementally better than a straight line, but if a straight line does a good enough job, and adding the extra term in complicates my analysis and my interpretation a great deal, it may not be worth adding that in, right? Again, because our statistical models represent they're supposed to be a useful tool to get a simplified version of an outcome that help us understand sort of general associations and things like that. All right, so we're looking at our multivariate, fully multivariate GLM. I've got a number of continuous X's and continuous Y's. We're looking at some canonical correlation types of analyses. If I've got multiple categorical X's and continuous outcomes, we're working with ANOVAs. Actually don't see a lot of ANOVAs anymore, but I know, so Allison, I was joking with Allison about this. I was like, oh, we do ANOVAs sometimes, right? We have kind of cut that out of this just because, but as long as you understand sort of multivariate general GLM stuff and ANOVA, you're good to go. Sort of ANOVA is not that much different, but this is what we see. If we got a mixture of categorical and continuous IVs and a number of continuous outcomes, talking about Mankova, we got discrete outcomes and a number of continuous observations. This is repeated measures ANOVA stuff. This is a big tool that hopefully many of you will be using in terms of thesis, dissertations, and things along those lines. Super powerful and helpful. If we've got a latent X, we've got X's that we've not observed, but a number of continuous outcomes, talking about factor analyses, principal components types of stuff. And then we've got a number of sort of mixed, continuous, latent X's, a number of continuous categorical latent outcomes, talking about some SEM types of things, right? But for the purposes of applied analyses, SEM path models, a lot of the stuff we do factor analysis isn't any different than just general sort of regressions. If you have a good understanding of regression, you're going to be well equipped to advance beyond this class into some SEM types of topics. Questions on any of this? All right, welcome back. This was Laura's class. They didn't know who He-Man was, and so that was a residual from there, but I just like having He-Man on there, so you guys get He-Man too. We're gonna roll into the next lectures. Don't touch that.
All right.
All right. People feeling okay with general introductions with that stuff? Good questions.
So I just have a question about the, I'm trying to remember what he was called, like the planes.
Yeah.
So that's just saying that sometimes you don't need
Yep.
all those different.
Yep.
Okay.
It depends on where your outcomes exist in multi-dimensional space,
Okay.
and so but you don't have to worry about the linear algebra or the geometry of all that stuff.
Okay.
Just trying to demonstrate that just because you have it doesn't mean you need to use it all the time,
Yeah.
right?
Okay.
And don't get worked up and trying to. It's not going to be on a test. I'm not I just wanted to for this. Introduce you to kind of some of the ideas. So if you run it down the road, you're back, okay, so at least know that this is a thing.
All right.
Okay.
Got it. Cool.
All right. So I'm going to spend some time jumping into basic correlation stuff, and then matrix algebra. We're not going to do matrix algebra because we've got better things to do with our time than linear algebra. I was forced to do matrix algebra in my multivariate class, and then didn't feel like that. Of time with everything else we got going on, so no mention. Has anybody had a linear algebra course? Not still? Okay, right. So you guys are already got it under control, right? But it's just basically the foundation for a lot of the stuff we do, but I won't make you find the derivative of matrices for this class. So what we'll talk about is correlation. Talk about correlation. Has anybody not been exposed to basic correlation stuff? Everybody basic understanding of correlation? Okay, cool. So we're talking about correlation. Looking at a measure of association, and this starts to become important, will be relevant to understanding some of our assumptions. Technically, when we're talking about a correlation, we're talking about association between a random variable x and random variable y. If I'm talking about a random variable, what am I talking about a random variable? No.
You just pick it.
kind of just pick it, yeah.
It's not deterministic.
What's that?
It's not deterministic.
It's
It
not
will-
deterministic.
Yes,
right?
it will have variation somewhere.
Lots of variation, right? So if we want to get somewhere, we just say just pick it, right? There's not some predetermined number of values that I'm going to get, right? It's a truly random variable. If I go through and just start closing my eyes and just like picking people out of Prexes, that's a random variable, right? I'm not saying I need so many of these, so many of this, right? And so when we're looking at correlation, we're looking at the association between a random variable x, random variable y, and we're assuming a bivariate normal model of sampling error in both x and y. Okay? This is going to be different than regression. At least in psychology, we often treat correlation and regression as interchangeable, and that mostly works for the most part in most situations. But technically, from a model-based standpoint, with a regression model, what we're doing is we've got a statistical model where some fixed variable x is used to predict some observed values of random variable y. Okay? So random variable y is just a pick of, what are we talking about in terms of a fixed variable x? Random variable y is just sort of pick them whatever. What are we talking about in terms of a fixed variable? Yeah.
You're interested in the specific relationship between this one thing that you've selected and some other thing.
Yeah, close. So what we're doing with a fixed variable is I would say, let's say, I'm looking at, so you're looking at, I know this is not a great example, but let's say that you're looking at,
Oh, I know one.
what,
Like measures on a social anxiety scale and eating disorder severity thing.
how about this? Let's say eating disorder severity, right? It's a random variable, but what you want to do is have, let's say for different sort of at increments of 5-pound intervals for body mass, right? So I would say, I'm not going to randomly select people who just kind of walk in through the door with some level of body mass. I'm saying I'm going to get 10 people at 90 pounds, 10 people at 95, 10 people at 100, 10 people at 105, 110. So it's systematically choosing in a theoretical sense, you would have representation, systematic representation of all possible values within sort of whatever your outcome was, right? So it's a fixed variable, and then I'm not just kind of accepting whatever comes in. What I'm doing is I'm specifically fixed if x is fixed. Okay, this is not the way we ever run regressions, but it's the way regressions were developed, and we start to run into issues with our underlying statistical assumptions when x is not fixed, when x is random. It works out as long as certain things happen, but it's technically a violation of the underlying assumptions. We'll talk about this when we get into regression stuff, but sort of thinking about this is the functional theoretical difference between correlation and regression. Correlation is just an association. I'm looking at sort of random variable x, random variable y. I'm just looking to see if there's a relation between the two things, and I'm not worried about any type of sort of causality or prediction or anything like that. Regression, we're specifically trying to predict some outcome with a fixed variable x for a random variable y. Okay? And with our linear regression model, we're assuming only error in our outcome, right? An assumption of our linear regression is that we are measuring our predictors without error. Do we ever measure our predictors without error? No, that also starts to screw around with stuff, right? And so we technically don't have distributional assumptions for x either in regression, right? If x is a truly fixed variable, if I went through and I systematically selected people for every 5-pound increments, so that I had 10 people for every 5-pound increment from 90 pounds to 160 pounds, what would the distribution of my x look like? My x's weight is flat, right? But, and is flat a normal distribution? No, right? But technically, regression doesn't have any distributional assumptions for the x because x's should be fixed and measured without error, right? So some fundamental differences between those two. We use regression like we use correlation, particularly in, in a lot of applied applications, but understanding sort of the difference between these will start to become important when we get into the underlying assumptions. So, we're going back to not worrying about regression right now. We're going back to correlation. Random variable x, random variable y. Our correlation coefficients are going to be bounded by -1 and 1. Our value is going to indicate the magnitude of that association, and we can also start to make some inferences about the direction of that association depending on sort of what the data are looking like. Sometimes it's kind of arbitrary on a scale, right? So I've got a scale where high scores are associated with low levels of support and low scores are associated with high, but it's random, I can switch them around, right? So based on the nature of the data, we use that sign to sort of make a determination on the direction, right? But this starts to become important, right? Last semester, when you guys were working with t-tests and stuff like that, if you just told me that there was a difference between group A and group B, was I happy with that? Guess why was I not happy with that?
You didn't say what the difference.
I don't tell you, you say the difference is like, oh, these two things are different. Well, tell me more. I want to know more things, right? Same thing. When we're working through this stuff, you just say that x and y are correlated with one another. We said, I want to know what direction. So, like, what does that mean? What's the covariation? As one increases, what happens to the other based on the data? Okay. And what do you guys got going on over the weekend? Super Bowl, probably. If you want to get crazy, the link down there, the game called Guess the Correlation, right? We'll go through, work on a high score on racking up Guess the Correlation. You go through, you get sort of a scatter plot like that, you get to toss into what you think the correlation is, and then they'll tell you, like you lose lives, you win points and things like that. It's a good time. It's a good sort of set a challenge. I want to see who can get the high score. Get someone Burger King crown if they sort of get the high score on Guess the Correlation. It's actually friggin' hard. So
You have to guess what the R is. Just like on the dot, you just have to be like 0.82.
Yeah,
That's insane.
it is insane, right?
Yeah.
It's so hard.
Oh, that's probably that. Oh, that's good.
On the street.
Oh, you have to be.
All right. New game.
Oh, no.
Okay. But you're gonna sell my ability to predict correlations with. Okay. Yeah, what do we think? What's the correlation here?
It's like 0.38.
0.38. Nick says 0.38.
No way.
Point two.
What?
1. 0.21.
0.21.
Yeah.
Oh, that's good. Nice. All right. Oh, what do we think?
0.75.
So I think it's bigger than 7.5.
0.95.
0.92.
0.92.
I like it.
9.2.
Are you serious? You're gonna go 9.2?
Oh!
You gotta wait until
That's right.
after to
Right?
make fun of them to make sure that.
Oh no. Okay. This one's tough. What about this one?
0.15.
That's like 0.15.
0.15. Okay. 1.5.
Nervous.
Ah, 2.1. Right. So, hours of entertainment. Hours of entertainment. What we're looking for is high score here.
But what's your high score?
What is the score?
I don't
Why is
know.
it 0?
Well, we haven't got there yet.
Let's play the new addictive clicker game.
Right? So, yeah. We got. I want to see photo evidence of high score, like you with a thumbs up or something like that.
You holding a spoon next to it.
Do you get bonus points?
Get a Burger King crown.
That's
I
pretty
promised bonus points in the past and then forgot about it, and then generally it doesn't make a difference.
Like when I found that picture of Sting at police.
That's true. That's true. I did. I gave you extra points.
Did I?
Yeah, you did.
Okay, cool.
All right. Cool. Finish up here with just some review on basic stuff. Variability. Remember, in general, when we're talking about variability just being the degree to which scores are spread out or clustered together. Okay. If scores are in a distribution all the same, there's no variability. We've got a constant, right? Everything's the same. If there are large differences between scores, large variability, everything's kind of spread out, right? And there's a number of different ways that we can think about variability that's going to be helpful for us. We can think about variabilities in index of a distribution. Think about it in terms of distance, right? How much distance do we expect between two scores randomly selected from a distribution, or between any individual score and the mean, right? So depending on what we're doing, some different ways to think about this, right? We can also think about variability as telling us how well any randomly selected score starts to represent the full distribution, right? So Simon, if I have a distribution that has a wide amount of a large degree of variability, and I select a random score from that distribution, is that score probably a good representation of representation of that distribution, or poor representation?
Poor representation.
Probably poor relative to a distribution that has less variability, right? And so we can think about, if we're using means-based statistics, we can think about variability as a measure of error, right? If I'm sort of interested in the average height of the average person on UW campus, right? And I know that there's a wide variability. If I randomly select one person, I know that there's probably a lot of error in my guesstimate of where that person is, right? Versus something that's, for example, what's going to be a better, Alicia, what's going to be a better representation of the larger distribution? The average height of an average person walking across, a college student walking across Prexy, or the average height, or the height of a kid in a kindergarten class?
Or
Which one's going to be more representative of the people here? Is there more variability in kindergarten height?
Oh,
or
sorry. No.
yeah?
No.
The kindergartner, right? So my kindergartner that I pick out sort of randomly, probably gonna be a reasonable representation of the average height of kindergartners, right? Versus random someone like walking across campus, we've got very, very large people, we've got very, very small people, right? There's gonna be a lot more error there, right? So thinking about being flexible in terms of how we're thinking about variability, in terms of distance from the center of a distribution, distance between any two given examples, thinking about it in terms of error representation. So this is all going to be helpful and useful. Okay? Variance, okay? Thinking about variance as the average squared distance from the mean, okay? Variance, not super useful in terms of just, scratch that. Variance, incredibly useful. Variance is essential to everything that we do. But in terms of thinking and communicating things to people, if I say, Nick, the variability of this is at 158, that probably doesn't give you any much information off the top of your head, right? So what we can do is we can switch over to standard deviation, right? We can loosely describe standard deviation or interpret standard deviation as the average distance of any score from the mean. Not exactly. Why can't we exactly interpret standard deviation as the average distance from the mean? Mathematical calculation. Yeah.
Because of error? Oh.
It was a nice try. It was a nice try. I see where your head's at, right?
Yeah, positive and negative.
It's just the average, the net average value of the differences between each of the
Right.
observations and the mean.
It's a technical issue, right? Remember that when we're calculating our variance, right, what we've got is we've got our x scores here, right? And what we first do, we calculate a deviation score. So if our mean is 6, we take our x, subtract the mean, right? Gives us a deviation score. And then what we do is we square each one of the deviation scores. Tomorrow, why do we square the deviation scores?
Because if we didn't, they would add up to 0.
Yeah, because what we're going to do is we're eventually going to sum those squared deviation scores to get our sum of squares. Sum of squares is just a sum of our squared deviations. If we didn't square them, by definition, they turn out to be 0, and that's not super helpful, right? So what we do is we square these, add those up, and then we get our sum of squares, okay? CJ, what's our sum of squares? Conceptually. What's it? It's a measure of
Variability.
It's just a measure of variability, right? It's just a really raw measure of variability. Is it interpretable? Not really, right? It's important for calculation, but it doesn't. I can't look at a sum of squares and tell you whether that's indicative of large amount of variability or a small amount of variability. But what I can do is I can take that sum of squares, if I'm calculating a sample statistic, and I take that sum of squares and I divide it by n minus 1. Why do I divide it by n minus 1?
Yeah, because it's a sample, not the population.
Exactly, right? Remember that our sample is never going to be as representative of, so it's never going to capture the distance of scores as our population. It's always going to underrepresent it. Now, if our sample starts to get really big, what happens to the bias in our statistic? Starts to go down, right? But if I start to have very, very small samples, the bias can be quite large. So I'm dividing by the number of individuals in my sample minus 1 to downward correct for that potential underestimation of the true variance. And this is why we can't technically interpret standard deviation as the average distance from the mean. It's not the average distance, it's sort of n minus 1. So there's just a small, it won't make a difference if I have samples of hundreds of people. If I have smaller samples, it will kind of make a little bit of a difference, right? So we go through, get our variance estimate here, and then we take the square root of our variance estimate to get our standard deviation. Standard deviation starts to be meaningful in terms of, if you tell me the standard deviation of height for students at the University of Wyoming is 3 inches, that tells me, okay, if I were to randomly select 2 individuals just walking across Prexes, I would expect their height to differ by, on average, about 3 inches, right? Or I could say I would expect that I just grab an average person walking across Prexes. I would expect their height to deviate from the mean on average by about 3 inches, right? Or I would expect there to be about 3 inches worth of error of that person from sort of the population mean, right? So we can start to use that. But if we're looking at sum of squares, variance, standard deviation, all of these are just going to be measures of variability, just kind of taking a different form, and some just end up being more useful for communication and calculation than others. And there's a computational formula there. All right. That does it. We'll jump into 5 o'clock. It's just like my timing is impeccable. Jump into covariance stuff next Wednesday when we come in. So we will. What I'll do is our first problem set we'll cover these first 2 lectures. So we're not quite through all the stuff yet, but what I'll do is get that problem set posted tomorrow. Try and get that up there. So it's up there for you all to start looking at and working on. This first one isn't going to be terribly taxing, but take it serious. I think that's not that you wouldn't take it serious, but just so be thoughtful as you're going through and working on stuff. It's not, so I'm not gonna have you work with like SPSS or data or things along sort of like data sets. It'll be more sort of conceptual and hand calculation types of things. But as always, just give yourself, this is, and you can talk with people, like these, start on these sets sooner rather than later. They tend to take longer and be more labor intensive than you might expect on the front end. So yeah, I'll go through, sort of take a look early, and again, guys, sort of, feel free to reach out with other people, sort of work on these and sort of collaborate as you're working on this stuff. So, but this first one shouldn't be too big.